Good morning, everyone. My name is Alex Kreese. I'm a senior content engineer here at Markforged. Marco is going to be helping us run the webinar today. So today is our Markforged University Seminar on selecting the right fiber for your application. So the first thing that we'd like you to do is fill out a poll you should see in front of you about how much you use fiber and what kind of role you have at your organization.
All right, poll should be up.
All right, so we'll give you a few minutes to answer that. Basically, today this webinar is going to be a bit different from your usual. There's going to be a couple polls like this, a few interactive elements. As Marco mentioned, feel free to use the Q&A window or the chat box if you have any questions or any comments over the course of the webinar. And we'll get started. So last Markforged University webinar, if you missed it, we discussed the basics of fiber reinforcement, basically how to lay fiber within your part effectively. So today we'll be building on that by talking about how to select the right fiber based on your use case and your applications. How are we doing on the poll, Marco?
Poll looks to be going well. About 70% of folks have voted.
Okay, great. We'll leave the poll open for about 30 more seconds, 30 more seconds, and then close it off. And right. So thank you all for submitting your poll responses. So basically, what we're going to be talking about today is what questions we need to ask to evaluate a part. Basically, in a lot of different applications when using our printers, it's really not about the application that drives the fiber selection. It's about what the loading conditions are, what the environment is. So here we have a part from a customer of ours, Humanetics Innovative Solutions. They are a leading manufacturer of crash test dummies. So it's a mold for this neck ring that you see right here that seats inside of a crash test dummy and helps protect these electronics and other components inside the dummy. So in order to understand what material we should choose for reinforcing this mold, I just wanted to open it up and ask, what kinds of questions do you think would be valuable to ask about this part to understand what it will go through? And please feel free to use the Q&A or the chat box to submit your thoughts on what you'd need to know if you knew that you needed to, again, this is a mold for for this neck ring over here. All right, so we have some people coming in asking about what heat is generated. So that's a really good question. This mold is how the process works is they put the mold together, they pour this thermoset material into it, and what they do is they put it in an oven and they bake it for about 36 hours at 150 to 200 degrees Celsius. With that in mind, we sort of gain that insight for what kinds of environment and what loading condition we can work with this part under. So yeah, we're getting some great responses in. Basically these questions are really about like what we need to ask. What is its failure behavior? How would we want a part like this to fail? There's another loading case here where this part gets bolted together, so that's an important consideration. We basically need to think about that with each of these applications because that's sort of how we need to think about each part. So a few learning objectives for this webinar is basically understanding what we'll be doing today is the key properties of basically understanding the key properties of each type of continuous fiber, assessing the environment and the loading conditions of a part, and enumerating that part's material needs based on its environment and then selecting a reinforcing fiber that is best fit for its application. So let's basically go over the sort of the 4 fibers that we have here that you have available to Markforged 3D printers. So we have these 4 different types: carbon fiber, fiberglass, Kevlar, and HSHT fiberglass. They each have their own pros and cons that make them more suitable for certain applications or loading conditions and less suitable for others. So we're going to go through and talk about the properties and benefits of each of these fibers so that you just have that sort of background knowledge. So here's on the left here we have, we're talking about fiberglass. So on the left of this video is a fiberglass reinforced onyx composite beam printed on a Markforged printer. Second from the left is an onyx thermoplastic. And just 1 minute before we continue, if you have any questions or filling out the chat box, make sure that you make the question available to all panelists, not just the moderator and attendees. That way I can see them as they're coming in. So just wanted to clarify that before we continue any further. Make sure you have all panelists selected. So back to fiberglass reinforcement. Basically, we have fiberglass here on the left. We have onyx without reinforcement next to that. And the other 2 here we have are ABS and PLA, which snap under loading. This is a 7.5 pound load hung from each of these beams. And you can see here that the composite beam with the fiberglass reinforcement deflects only slightly and then returns to its original state after the weight is removed. So first off, we can see the difference between composites and strong thermoplastics. That's best illustrated by observing even the unreinforced beam, which has chopped carbon fiber inside of it. Although onyx is stronger than most other thermoplastics, when reinforced with a continuous fiber like that fiberglass, you make the part a lot stiffer and less ductile. So this is just with fiberglass, which we consider to be sort of an entry-level reinforcement fiber. It's already 3 times stronger than ABS and less expensive than the other fibers. So it offers sort of a good starting point for stronger parts. And we can see that in the numbers too. It's about 3 times stronger than ABS and about 6 times stiffer. So one thing you'll notice in the video is that the fiberglass reinforced beam does bend a bit when loaded, but it returns to its original state. So it has some energy return and springiness, and basically how it fails is that it bends until it fractures. So it'll have some give before it'll break. And when we discuss the key properties of fiberglass, taking from that information, it's basically just a robust and sturdy starting fiber. When you need something that's stronger than your average thermoplastic, but don't explicitly need super duper high strength or stiffness, it has some flex and energy return, as I mentioned. And basically what we think of as an ideal loading case for this is what's called intermittent loading, where your part will undergo regular repeated loads of roughly a constant force. And that's because of the energy return and because of that flex with when it's loaded. It has a little bit of give, so it's sort of a little conformal. So next up we have carbon fiber. In this video we're actually hanging 27.5 pounds from this carbon fiber reinforced beam. And you can see that, and next to it we actually have an aluminum beam of the same dimensions. You can see that the composite part basically minimally deflects and then returns to its original form, while the aluminum beam yields under the load and does not return to its original state. So one interesting thing to note is that the strength of our 3D printed carbon fiber is high enough that it's equal to the yield strength of 6061 aluminum, meaning that it fails at the same stress. So it fails at the same stress that aluminum plastically deforms. So you can use this as a good substitute for aluminum parts. One of the cool things about this is that the carbon fiber beam is 7 grams and the aluminum beam is 12 grams. So at just about half the weight, you have the same strength. So carbon fiber is really where you want that high strength and low deflection. Generally, it can be used as a substitute for aluminum parts, as I said. It has the best strength to weight ratio out of any of our fibers, with a specific strength that's about 50% higher than that of 6061 aluminum. to sum it up, it's our stiffest fiber with the highest strength to weight. How it fails is it basically stays stiff until it fractures, which happens usually abruptly. This makes it more ideal for sort of constant loading, where it's supporting a known force all the time. And while we're talking about ideal loading conditions and failure behaviors, it's not that carbon fiber isn't good for intermittent loading. It'll probably hold up just fine depending upon the use case. It's just that constant loading is the area in which it's sort of best suited, and it can really shine. So our next fiber is Kevlar. Kevlar is extremely durable and impact resistant, which means parts reinforced with Kevlar can take a beating without fail, as shown by this video here where we're smashing this Kevlar part with a hammer. For reference, the blue part is ABS, the red part is PLA, and the black is Kevlar reinforced onyx. Kevlar is also pretty unique in that it's 15 to 20% less dense than the other three fibers, making it the lightest of our reinforcement, not to be confused with strength to weight, it's just the lightest fiber. Kevlar also has the ability to plastically deform without losing strength, and that's because it's super tough and super impact resistant. So it retains high strength while allowing some give and some energy absorption, essentially. And it has the least catastrophic failure mode of the rest of the fibers. So while carbon fiber sort of fails completely and almost with no warning when loaded to its maximum, Kevlar deforms until the fibers begin to fail one at a time. And that's because it's really, really tough. So it'll bend and it'll bend and it'll bend, and then eventually it'll just deform instead of snapping, which would happen with carbon fiber or fiberglass. So this provides a much more predictable and forgivable failure mode compared to the other fibers. And so again, it's lightweight. It's perfect for those impact loading scenarios where toughness is needed. One of the other neat things about Kevlar is that it's highly abrasion resistant. When reinforcing with fibers, because the fibers are going to be inside of your part, this doesn't always come up, but it's a neat thing to keep in mind if you need some highly abrasion resistant material to 3D print. The last material we're going to talk about is quite unique to Markforged, and that's high strength, high temperature fiberglass, or HSHT for short. Before this video that you see here was shot, each of these beams were heated in an oven to 140 degrees Celsius, or about 285 degrees Fahrenheit. So the HSHT reinforced beam, you can see here, retains its strength even with all that heat, whereas the PLA and the ABS ones essentially warp under their own weight. And so this beam here is shown supporting a 5-pound mass hung from its end, while the PLA and ABS basically you can see sort of deform and sort of flop to the side of the table right here. So it has this superior heat resistance, hence the name, and retains its strength up to temperatures of about 150 to 200 degrees Celsius, or around 300 degrees Fahrenheit. So it's well past most thermoplastics glass transition temperature. And the heat deflection temperature is about 80 degrees higher than any of our other fibers. The thermal properties of HSHT allow for applications where strength is needed at these higher temperatures. So that's really its big value. But one of the neat things about HSHT is that it has very, very high elastic deformation properties, more than any of our other fibers. So this means that it will deflect as it's loaded towards its maximum and return to its original shape when the load is removed. So if you need parts that really need to bend and be very springy, this is a fiber that you could use. And that happens more so than with fiberglass, where fiberglass is sort of a little bit springy, but HSHT really has some flex and some energy return that's much greater than that of fiberglass. And so because it's still very stiff, but it has a lot of energy return, it's pretty good for both constant and intermittent loading forces, like clamping or like any sort of grippers or sort of repeated impact loading cases. But it's also just generally can do all these and perform at high temperatures. And so that's basically the spectrum of our reinforcement materials and how they behave. So we can use these properties to identify which ones would be suited for good applications. And now what we're going to do is basically match those fibers to a variety of different applications and use cases. I'm not going to really tell you that one fiber will work best for a specific application or a specific use case, because it really is dependent upon the environment and the loading conditions that your part undergoes, and what you need for your part to be successful. So the needs of your part are really up to you to decide. So the next section is basically we're going to go through a couple different applications and discuss the material requirements of those applications, so you get into that mindset of thinking about the needs of your part. So this section is a bit experimental. We'll see how this goes. It's what we've got here is basically a Jeopardy style board, and beneath each tile is an application. So we're going to work together to uncover all of the tiles on this board and identify what fiber would be best fit for each of these applications. So again, I'd very much like this to be a discussion, so please feel free to ask questions or submit comments in the chat box when these applications come up. One thing to note, as I mentioned before, is that right now I'm a panelist on this webinar, so I can only see questions that are and comments that are directed to all panelists. So please make sure that if you're commenting, that you are, or if you're asking questions, that you're asking toward panelists. And Marco's going to help out with supporting that here. Are we all good on that?
Yep.
Okay, great. So when we uncover each application, we'll have a poll go live where you can sort of guess what fiber will be the best fit for that application. And then we'll sort of wrap each one up with a discussion about what that best choice would be. And at the end of the discussion, once I go back to this board, I'll choose the next tile based on whoever responds first with an application area and a category. So I'm going to pick the first one over here, tooling and fixturing for 100. So this is basically what I said before. This part is a familiar one. It's a thermoset mold. It basically gets the part gets put in an oven at about 200 degrees Celsius for 36 hours. So is the poll live?
Live right now.
All right. And so I'm gonna have this open as we talk through it. Please remember to submit any questions or ideas and vote in the polls what you think would be the best fit. One thing they actually did before Markforged, as you see in this photo in the lower right, is that they would machine these very complex silicone molds. It's not the exact same one as the mold that they printed, but you probably get the idea. They had to make a mold for every one of the thermoset parts in the dummy. And the silicone molds were degrading over multiple cycles because of that heat and that wear. And
if you can't see the poll, there should be a polling button in your interface down at the bottom that you can click to open the poll.
Thank you, Marco. What Humanetics actually did here was they tested this part just in onyx just to see if it would work. But after a while, the material started to lose strength and warp after repeated cycles in the oven, which is why they chose to reinforce it. So let's look at the poll and see what people think the right fiber for this would be. Marco, what are the results?
So it looks like 88% picked high strength, high temperature fiberglass, and the second runner-up, or the first runner-up, was Kevlar with about 7%.
Okay, great, thank you. Yeah, so HSHC would be a really great choice for this application because it's a mold and it's being put in this oven at a high temperature. What we really need to do is make sure that the part maintains its strength at that temperature. If it were just functioning at room temperature, then it would probably be okay as it is with just onyx. But putting in the oven caused that thermal warping, and that's what and that meant that HSHT would make sure that the part sort of held its structure. So if you think of the fiber as a bone, the bone is essentially making sure that the part is staying as is at these high temperatures. And some people put Kevlar as sort of the runner-up here. Kevlar would be a good choice because I do say that there needs to be some easy release of the part from the mold, and there's some small clamping force from the bolts. Basically, one of the things that's interesting to note about these is that if they were to machine these out of aluminum, they would have had to have a much more complex mold that was going to be really expensive to manufacture because the mold would have had to be rigid. But because of the onyx, it can be just ever so slightly flexible. That's why it's sort of shaped in this way where it's not a big block. It's actually this thin section so that they can flex it to release the part from the mold easily. So Kevlar would be a good choice if you do need that flex, but the primary material constraint here is that it can withstand the 200 degrees Celsius heat in that oven. So thank you all for submitting. And so yeah, HST fiberglass was what we wanted. So again, we're going to go back to the board. Once I get back to the board, the first response that I see come in the chat with all panelists, I'm going to go with that one. So submit your ideas here and please use the chat box. All right, so the first one that we saw came in was 200 for tooling and fixturing. So this one is a CNC machining soft jaw. So what do all of you think would be sort of the loading, what are the loading conditions that we have to think about with this CNC soft jaw? It's this, in the middle here, it's this, this black part, and you can see it sort of in a more simplified view here. So if you have any thoughts about what the loading conditions are, please post them in the chat box. All right, so basically the four main things that we have to think about here are there's a lot of things coming in about accuracy. It's sort of an intermittent loading condition. There's a clamping force from the vise closing around the part, as well as sort of loading from the z-axis due to the tooling. Is the poll live now?
All right, let's relaunch that.
We're gonna launch there's some vibration. That's a good point coming in from the machine machining that part. So we have that poll live, so please vote, and we'll talk through our submissions. So yeah, there's some deflection in case of part deviation or some vibration. There's pressure from those applied machining forces. And there's also a little bit of heat buildup from machining, but that's sort of a secondary goal. And let's look at some other comments in the chat here, just so I can go through. One person did point out that there's going to be some amount of intermittent loading because if we're machining multiples of these parts, we're going to be opening and closing that vise a lot over the course of those machining cycles. All right, should we close up the poll?
Yep, so it looks like a majority did vote, so let's share those results.
All right, so this is actually really interesting. It looks like most people voted for Kevlar, with carbon fiber in sort of second and fiberglass in third. Actually, this part was reinforced with, let me make sure that sorry, I'm having some technical difficulties. There we go, with fiberglass. So Kevlar would be a pretty good choice for this as well. There's a lot of sort of vibration dampening going on from the jaws because the jaws are closing around the vise and the machine is sort of milling that part out. This part was actually reinforced with fiberglass, and that's because of that intermittent loading. The key constraint here is that we want the part to be well secured, and so the vise needs to be very robust. And so fiberglass would be a good sort of option for that reinforcement. Although Kevlar would probably do just as well, you may need to reinforce it with a bit more Kevlar than you would have with fiberglass, just because Kevlar is generally lower strength and will deflect under less pressure. But in general, Kevlar could be more sort of conformal. So I talk here about like if you were machining 100 of these and 5 of them were maybe a little off and the geometry wasn't quite right, then Kevlar would be able to sort of absorb that deflection a little more, but it would not be able to apply sort of as much pressure as fiberglass would because fiberglass is stronger. So great insights. Thank you everybody for voting. So again, we're going to go back to the board and let me know what you want to do next.
So it does look like there's a bit of a delay between when people type in their chat messages and when we receive them. So we're going to give it a minute.
Okay.
Here we go.
Great. So the first thing that I saw came in is prototyping for 100. So over here we have an end effector for a robotic arm. This customer is, and let's launch the poll so that we can just start getting those results in now. So end effector for a robotic arm, the key thing is that this is hold on, I gotta move things around on my screen. So this environment that this robot is working in needs to be highly controlled and contaminant free, because this robotic arm handles these semiconductor wafers for functional testing of their devices. So they have to basically machine their final part out of metal. But for functional testing of their devices, Brooks Automation decided to print these prototypes instead of machine them, so they could reduce their iteration cycle time and test out geometries a lot faster. So first and foremost, they need to make sure that this part behaves as closely to the final metal part as possible, while also gently handling these semiconductor wafers and precisely loading and unloading them from these trays that you see in this photo over here. So what fiber do you think would be best for this one? The other thing to note, as it says here, is they also need to minimize deflection and maintain a very high precision, because they have very high standards for how the arm needs to be able to handle the wafers and to what degree of precision it can place them in the trays. So do you have poll results in?
Yep, you're there.
All right, so a lot of you got it right. Hold on, here we go. The fiber that they used is carbon fiber, and as I mentioned before, that's really because of they need to mimic the properties of metal parts, and the best way to do that is with carbon fiber, because it can match the strength of aluminum, which is what they would have machined it, which is what they machined the final part out of. So let's go back to the board here, and again, the first thing that I see come up is going to be what I'm going to go with. All right, so the first one that came in was end use 100. So this is a customer called Media Blackout. What they do is they make specialized custom equipment for media companies. So this part that you see pictured here is a lightweight adapter for camera equipment setups. It basically serves as a robust connection point to convert one type of connector to another on their screen. And is the poll launched?
The poll is live. Okay,
great. And it also has to interface with these electrical components. So the part can't have any sort of, it can't have any, it can't be conductive. But the main things are that it's lightweight, it's robust, and one of the reasons why they actually chose to go with Onyx for this in general is that the Onyx blends in with a lot of the media equipment. It has to be non-reflective, so it can't produce any light, because you don't want anything to reflect off of it when you're filming or anything like that. So let's look at the results of this poll. So a lot of people put, actually it looks like we have a tie between fiberglass and none. So as I mentioned before, this is sort of a lightweight adapter for camera equipment setup, so it does need to be pretty light. It also needs to be pretty robust. But when it comes down to it, this part is basically just a connecting point. It doesn't really experience that much load. It's mostly just serving to adapt one thing to another, and the forces from the things it connects to are altogether not that extreme. So none is the right choice for that. I sort of threw in a red herring there, saying that it had to be robust and lightweight. One thing that you need to think about is that if you were machining this, it would still be very heavy out of metal. And so even just by 3D printing it, you're reducing that weight a whole lot. And if you don't need the requirements, the material requirements of metal, then you can just, or of like a really high strength robust plastic, then you can just sort of 3D print it out of Onyx. it's really that this part doesn't undergo any really high loading conditions. Even if it were dropped, it would probably be okay once it hit the ground. I'd be probably more concerned with the other equipment. All right, so thank you all for responding. Oops. So we're going to go back to the board, and again, let me know what thing you want to go with. Prototyping 200 came up first. So this is actually a really fun one. This past year, we sponsored a BattleBots team, Team Valkyrie, based out of Cambridge, Massachusetts. One of the things they did was, this is their robot in the bottom right here. And this is a bottom view of the robot here. And there's this skid pad here. This one isn't printed, but they printed the prototype for this with our printers. And the requirements for these are that it attaches to the bottom of the blade, so it's the third point of contact apart from the two wheels. And when the weapon spins, it spins against the ground at about 2,000 rotations per minute. So it spins really, really fast. It attaches to the bottom of the blade. They wanted to basically do a functionality test on the geometry of this skid pad because they wanted the teeth, the tips of the blade to just lightly scrape the ground. So that geometry, before they started machining it, is super important to get right. Before they started machining these final UHMW skid pads. So please let me know, fill in the poll, what type of fiber would you use in this situation? And one of the interesting things is that they had all these UHMW skid pads, and they went through about 7 fights over the course of the season on BattleBots. They had a 4-2 record. And by the end of the season, they actually had to end up using that printed prototype because they were out of the UHMW skid pads. So let's look at the results here. So a majority of the people voted for Kevlar. That's right. I sort of mentioned earlier that Kevlar is a very abrasion-resistant material, and what you can see here in this photo is this is where we can actually make use of that. The onyx actually wore down as it was spinning against the ground, but the Kevlar stayed strong. So they sort of made use of the abrasion-resistant properties of the Kevlar by letting the onyx wear down so that it was just sort of a Kevlar plate instead of a onyx one. Some people also put carbon fiber. That is a good idea because it does need to support a whole lot of weight. But in general, this part ended up being just packed to the brim with Kevlar. So it wasn't going to, it basically just needed to sort of hold strong and resist that abrasion. All right, we're going to go back to the board here. And please let me know what you want to look at next. All right, so we have tooling for 300 coming in. And my mouse is being a bit weird, so I'm trying to click on it here. What is going on? Hold on, I'm having some technical difficulties. Sorry, everyone. Just trying to figure out. Okay, I'm just going to skip to it because for some reason it's not letting me click on it. So tooling for 300, this is an inspection fixture designed by J.J. Churchill. And let's launch the poll now so people can look at this. The key components that we have here, the key loading conditions are this clamping force from the bolts clamping into the table. We have to have this pretty secure grip on the turbine blade that they manufacture. So they use this inspection fixture to basically validate the geometries of this turbine blade that they manufacture. So what they need is they want to get a good result from the scan of the blade. So they need to minimize the deflection of the part as it sits in this this fixture so that they can maximize inspection precision. Because any small, there are very small light pressures from the inspection probe. So overall, this part is not experiencing a whole lot of external load. It's really more of a statics problem of making sure that this blade that's going all the way sort of standing upright will not deflect during the inspection process. All right, so let's look at those results. And let me make sure I bring them up. So a lot of people put carbon fiber here. A couple of people put fiberglass as well. So carbon fiber or fiberglass would both be pretty good choices because, again, you sort of get that robustness, that strength, just to make sure nothing moves. I would say carbon fiber here would be the better choice because you want to minimize deflection as much as possible. So even if by accident there's some pressure on the tip of that turbine, the carbon fiber will, because it's so stiff, will be able to sort of reduce that and make sure that it stays stiff and it stays in the same place the whole time. Right, we're going to go back to the board. So remember, tooling and fixturing 300 we just did. So if you have any thoughts for the next one. One person did bring up a good comment about thermal expansion issues with plastic in metrology. So in general, because of that reinforcement and because of the onyx material, the parts are very dimensionally stable. So you're not going to see that much expansion or anything like that because the materials, basically, the carbon fiber, both in the onyx and in the reinforcement, will essentially ensure that the part stays dimensionally constant. All right, so the first thing that came up was prototyping for 300. So I'm going to go down there. So this is a really interesting application, actually. It's very different from what we normally see our printers being used for. It's a stroke mobility device. And how this device actually works is basically when someone is affected with a stroke, usually one side of their brain is affected. Walking is a naturally symmetrical brain activity requiring both sides of the brain working together. So depending upon where the lesion from a stroke occurs, it can prevent signals from going through the brain properly. So you basically may need to relearn how to walk with a new gait to make it symmetrical again, because your brainwaves aren't necessarily communicating from the left to the right side of your brain anymore. So a lot of the devices that currently help fix this are really fancy treadmills that may be kind of inaccessible. And this device, what they're working on, it's in clinical trials right now. You mount it to a patient's foot and it supports them while they walk on the ground and adjusts their gait with these sort of springed cam mechanisms here while they're walking to help reteach their brain how to walk. So it's a much simpler, more cost-effective solution than what's currently out there. And they print these devices for prototyping while it's in clinical trials. So basically the design constraints for these are that it needs to support the weight of a person from these multiple contact points, and it needs to be capable of handling gait-related loading conditions and impacts, but light enough to not further impair gait. Again, because this is a learning device, it's sort of, in the case of a fall, the part may need to endure that. So please think about what type of fiber you'd use to submit in the situation. If we have enough polls in, then we'll look at the results. So the results here, a lot of people put fiberglass. Looks like people mostly put Kevlar. About 53% put Kevlar, 33% fiberglass. And let me make sure I can click to the next section. Oh, whoops, I already did that. So they actually used, sorry, this information's wrong. They actually used fiberglass for this one because they really wanted that robustness and the rigidity in these cams. I think Kevlar would also be a very good option. So for this, because it needs to endure the sort of the impacts from walking. Fiberglass is a more affordable solution, as somebody actually mentioned in the chat box. So going with that is sort of the starting fiber, just getting a really robust print to work and to function in this environment is a way to go. So in some cases like this, there's not always a go-to fiber that's exactly the right one to use. A lot of times fiberglass and Kevlar, it's really up to your preferences and your prioritization based on what, in terms of selection. So Kevlar could be good because it has that impact resistance and that durability, but fiberglass could be just as good because it's very robust. And it's also very cost effective if you're looking to reduce the price of something like this, but still have it be reinforced. So we're going to go back to our board here. Please submit what the next section you want to work on. We just have the 2 remaining ones in end use right here. All right, so 300 for end use. So this is an arm that is built by Haddington Dynamics. It's a 7-axis robotic arm. The joints, they actually print the optical encoders on their joints, and their joints end up having 50 micron joint precision because of the electronics and that they're able to work in there. It supports a 3 kilogram payload, and they actually have 70 3D printed parts on this arm. So let's launch the poll, and we'll also talk a little bit more about this arm. It's what they strive for is this sort of low cost precision pick and place machine. And so what they really care about is that precision, making sure the arm can get down to really fine accuracy. And the joint precision is dependent upon both their sensors and the hardware that they have inside their machine, and it's also dependent on the material that they use to make all these parts out of. So all the way up and down the arm, all of these parts, all the black parts that you see, are 3D printed and reinforced. So let's look at what people think for this application. So majority of people put carbon fiber. Some people put fiberglass. Carbon fiber is what they ended up going with here. Carbon fiber is what they ended up going with here for 2 reasons. One of them I actually didn't mention in the slides. The first is that precision. The precision is dependent upon the stiffness of the joints and all the limbs of the arm, all the sections of the arm. So it needs to be really stiff so that if a component moves, if a part of the arm moves due to actuation, that movement is not when it moves, you basically want the whole arm to stay stiff and not to wobble or flex or anything like that. So because carbon fiber has the maximum stiffness of all of the materials, it will allow for that. And also you want the arm to be really light. So if the arm was heavier, then it wouldn't be able to move as fast, and it would also only be able to support a smaller payload. So by printing all these parts with carbon fiber reinforcement, they can make the arm really stiff and rigid, but also really light. Some people did say that fiberglass would be a good option for this. That's true, but because they prioritize stiffness, you need to put more fiberglass into a part than you would carbon fiber to achieve the same stiffness in your part. So that's one thing also to think about in terms of reinforcement is, yes, fiberglass could be a cheaper option, but in terms of material consumption, you will need to use less carbon fiber to make something as stiff as you need it to be, whereas you may need to use more fiberglass or more Kevlar if you use those options. All right, so we're gonna go back to our board here. And we have end-use parts for 200 is the last one, so I'm going to go ahead with that. So this one, back to Humanetics, this is the same company that we talked about earlier with the neck ring mold. So this is a crash test dummy for, basically they 3D print the ribs for their crash test dummies. The ribs see some of the highest stresses during a crash, so they're the most likely to break. and you have somewhat unknown loading directions. Previous plastic iterations failed after about 20 impacts, and they wanted to increase the lifespan of these ribs by 3D printing them. So please enter in what kind of fiber you'd think would be right for this situation. And yeah, as I said, this is a really interesting application. So it's very high impact loading. A lot of these crash test dummies are used in all these sorts of conditions. So you don't really know what how this part's going to be loaded. So let's look at the results here. So it looks like most people voted for Kevlar in this situation. That's correct. This part ended up using Kevlar. As I said, the key thing here is that they're getting these like odd impact loading conditions from all these different directions. So first of all, the rib is structured to be able to handle that. When they 3D printed it with Kevlar reinforcement, they were able to bump up the cyclic lifespan of the part from 19 cycles to 70 cycles. And that's because, you know, the important thing here is the failure. Is being able to understand how the part will fail if it does, which because Kevlar deforms, it's not going to be a dramatic fracture or anything like that. So it's easier to predict what will go wrong if it does. And it's also going to be a very robust fiber when it comes to impact. So it's really, really tough, and it's going to be a really good choice for this. So that's the end of our board. So now, oh, whoops, I did not mean to do that. Okay, so one of the key takeaways here and why I sort of walked you through all these examples is that there's not one go-to fiber for a specific application group or industry. It's really up to you to decide what fiber will work best based on the needs you have. And the way to do that is by just thinking critically about the environment you need your part to succeed in. So this is just sort of, this exercise is just to get you thinking in that mindset of looking at an application, being able to pick out what the important aspects of it are, and thinking critically about that environment and those loading conditions, how you want it to succeed, how it should fail if it does fail, and overall what behaviors you need it to have. And then match those prioritized loading and environment needs to fiber properties. So as I said, sometimes it's a choice between things like fiberglass or Kevlar or HSHT or carbon fiber, something like that. And it's really up to what loading condition need you prioritize the most. So if you need it to perform best at high temperatures, then HSHT is the way to go. If you care more about how it survives under impact, then that it can handle it can sort of stay robust, then Kevlar is a better option. So it's all just really about thinking about what your part needs and what you value as important for fiber selection. And one of the other important things about that is if you need your part to be stiff, there are multiple ways to solve that problem. Based on what fibers you have available, how much you're willing to spend on how much material you're willing to use for the part. So you can create a part that's just as stiff with fiberglass as you can with carbon fiber, but the amount of fiber that you use in each is going to be different. And the last thing here is that once you've done this prioritized matching of your environment to your fibers, is just being able to understand how to reinforce the parts effectively based on those loading conditions. So if you haven't seen our previous Markforged University webinar on effective fiber reinforcement, I definitely recommend that you take a look at that one, and it'll guide you through the basic steps to thinking about part reinforcement so that you can make your reinforcement cost effective and exactly as functional as you need it to be. We have one last poll for you. I just want to gauge some interest on what kinds of things you want to learn about next. Markforged University is a relatively new initiative, so we want to learn what we can teach our customers and what they would value as most what they see as most valuable. So one of those things, we actually had a couple questions come in about how do you decide the right amount of fiber to use after you know which fiber to use. So if you want to learn more about that, we actually have one of those options for materials and reinforcement strategies, and that's one of the ideas that I've come up with as a seminar that we could offer about how much fiber is enough fiber for your application. So if you're interested in that, please put that into the poll, and I'll happily look into that. And if anyone has any other questions.
Now, with the poll, I think if you have a specific idea about something you'd want to learn about, or if your option is not on that list, feel free to just put it in the chat box.
Yeah, thank you, Marco. All right. So any other questions or anything like that? All right. If there's no other questions, we're going to basically we're going to close out the webinar. I am going to leave it open for a few more, for maybe about a minute or two, just so you can put your responses in. But thank you all so much for attending. I hope you all enjoyed it, and I hope this was useful. Usually we try to run. We have a question in about when the next webinar will be. We usually try to run this about every month. I'd say we'll definitely let you know. We'll be sending it out. How do we inform people of the webinars?
So we send out emails, which is probably how you found out about this one. Right now, we're at a sort of about a monthly cadence for customer webinars. The next customer webinar actually is going to be next week because, and this is really interesting that it's happening today, we just launched H13 Tool Steel. So as of today, you can now, on our MetalX system, print with H13 tool steel. We did launch the MetalX with 17.4 pH stainless steel. And now, as of today, we're launching our second material, which is H13 tool steel. We did send out an invitation for that webinar today, actually just a few hours ago. If you did not receive it, feel free to get in touch and we'll send you an invitation to that. And so next week, we're going to have Brian Semple, our CMO, Julie Finkelstein, who's from product management and an application engineer, have a kind of a fireside chat about H13 and some of the applications, the properties of the material and things that you can do with it. But as far as these Markforged University Learning webinars, we do host them about every month or so. So I think we should expect the next one sometime in January, and you will receive an invitation to that as we prepare it.
Also, there are some questions coming in about more specific details about fiber performance and loading conditions. If you would like to learn more of those specific numbers, some of the ones that I showed in the over the course of the presentation, you can find those on our material data sheet, which you can download from our materials page on our website. So please check that out if you're interested in learning more about the specifics of each of our materials and their yield strengths and all that kind of information. We'll also be sharing this recording with you probably tomorrow, sometime in the next couple days, so that you can refer back to it if you want to.
All right, and with that, thank you for joining us today for this webinar. We hope you enjoyed the format. It was a little bit different today, but we had great engagement from everyone in the audience. So thank you so much for pitching in and contributing to the webinar, and we look forward to seeing you at the next one. Thanks so much and have a great rest of your day.
Thank you so much.